So that was a couple announcements before we start from students. I do want to be clear that I'm not endorsing a particular political party for SGA. It matters very little to me who wins, but the point of that was to make sure you guys know about the elections going on, and if you do care enough, please do vote, and they have the information about that as well. All right, so then we heard from Leonardo about Stop the Bleed training course, which is very good thing to get involved with. And then another one that was asked to pass along was HOSA, one of the pre-health organizations, having a general meeting Wednesday of this week. So I think some of the students in this class are involved with that as well. All right, but we're going to get on into the next part of our course. So we are starting Chapter 5 today. We finished all of Chapter 4 last week, which was on primarily covalent bonding and molecular structure and things of that sort. Now, before I start the chemistry, I do want to go over some quick information about how the exam went, so just to see where you guys stand. So here's the statistics. Basically the same as last year. So the average was 13 out of 20. Standard deviation 3.5, meaning that there was a bit of a spread in the score. Maybe it was 3.4 this year. I might have miswrote that. But anyway, pretty similar to last year. And that's sort of a look. There were, I think, about 4 people that got perfect scores. So that was great. So obviously we want more than that next time. Now, we talked at the beginning about what you have to do to get a good grade in this class and all that. And one of the things that we mentioned that was important was doing as many homework attempts as possible. We've encouraged that this semester by offering you bonus points. Now, that honestly is the one that's easiest for us to keep track of. There's obviously a lot more things that have to go into your studying and your personal preparation to get a good grade. I do want to take a quick look at how the homework statistics looks. There's a lot of scatter in this data because it still is early and we only have had 4 homework assignments to go with. There is still a correlation between the number of homework attempts and the exam score. So this plot here is basically showing, why is this, all right, I'm going to zoom out a little bit because I'm like, all right, that's better. All right, so this plot is showing how we have number of homework attempts on the x-axis. So these are, again, ranging from 0 to 16 because there were 4 homework assignments. This is tracked from the bonus score, so technically it's number of homework attempts that were better than 5 out of 12. That's the easiest way for me to track it, but almost all the attempts were above that. All right, and then the exam 1 score on the y-axis. So there's a lot of scatter in the data, so even people that did the maximum number of attempts had a wide range of scores. That's not terribly surprising, but there is still at least somewhat of a positive correlation. So if we use the slope of this correlation, what it means is that right now the average student is doing 3 homework attempts per week. That is significantly better than last year, so I am happy to see that the time on task outside of class is improving. Last year there was about 2 attempts per week for students, so we're doing better, but there still is some room for improvement. So if you did all 4 attempts, sort of the average. So if all of you did all 4, so in other words, if instead of the average being 3 attempts per student, it was 4 instead, that means every single one of you was doing every homework attempt every single week, our average grade would have probably gone up by about 8% or so. So there's still some room for improvement. And obviously, as I said, there's a lot of scatter in this data, so that's not saying that individual outcomes would have changed by that much. But we still think we could bring the class average up even more if more of you were partaking. I know a lot of you are, and I appreciate that effort. And obviously, as I said, there's a lot of other things that have to happen besides that. So if you are already doing the maximum number of homework attempts or very close to it, obviously keep doing that. Even if you're not happy with your exam score, that doesn't mean that has no value. But it also means that you need to maybe reconsider how you're approaching those attempts or what you do with the information that you get on which questions you get wrong and get right, and try to get more help outside of class. So there's a lot of ways we can change, and I'd be happy to talk about that with any of you. So this just gives you a breakdown of how things are going right now with respect to exam scores and homework attempts, and I hope that this will continue to improve throughout the semester. All right, so we're going to move on to Chapter 5 now, and this is where the course sort of takes a sudden and abrupt turn, hopefully for the better. So if you have the textbook, you've seen that the title of the textbook is Atoms First Approach. So we've kind of gotten through all the atoms stuff. Now we're going on to the rest of chemistry, basically. So we have started with going through atomic structure and how the electrons are all arranged in individual atoms, and then more recently we've talked about how 2 or more atoms can bond to each other, the orbitals that are involved, the structures that form, all that stuff about individual atoms, individual molecules. Now we're going to start talking about things that happen on larger scales, on large collections of molecules. How do we measure amounts of substances in a chemistry lab, or how do we talk about chemical reactions now and predicting not only what are the products of the reaction, but how much of them are going to be formed and so on. So we're really getting into now a more quantitative treatment of chemistry, where we're going to look at, again, amounts of substances on macroscopic levels, and in some cases relate that to what we learned at the atomic level. It's not that we're going to forget about everything we've done so far, but it really is going to be a lot different approach, a lot more numerical, as you guys will see. So the first concept I want to introduce in this is what's called atomic mass. So this will be kind of familiar to us because we've already talked about mass number, which is the number of protons and neutrons, and this is related to that, as we'll see, but there are some differences that are important to keep in mind. So the way that we measure atomic mass, you could measure it in grams, which is the standard SI unit, but that would be very tiny numbers for individual atoms. So we use what's called the atomic mass unit, AMU. And the definition of the AMU is we take the mass of the carbon-12 isotope. This one was used because it's very common, very easy to measure, and we divide that by 12. All right, so in other words, the mass of C12 is exactly 12 AMU. And then we set that, we kind of standardize that for all the rest of the elements. So the standard is again, carbon-12, and then all atomic masses are measured relative to this. It is, as you might understand, difficult to measure the masses of individual atoms in an absolute sense, but we can measure them relative to each other pretty easily. There's a technique called, we're not going to go into it, but there's a technique called mass spectrometry, where you basically make ions and then you deflect them in an electric field, and the amount that they deflect in the electric field is dependent on their mass, and that's how you can measure relative masses of things, even though the absolute mass can be difficult. So if we have other isotopes besides carbon-12, either other elements altogether, or in this case another example of the carbon isotope C13, we know from what we learned before that C13 just has one more neutron. It's, instead of 6 protons and 6 neutrons, it's now 6 protons and 7, so you just add one more neutron, which increases the mass number. If we wanted to get the mass of 13C in AMU, what we would do is we would take the ratio of the two, and find that it's 1.0836. And so then if we want to find the mass of 13C, we take this number and multiply it by 12, because again, the mass of carbon-12 is exactly 12. That's the standard that we set to. And what we get is, not surprisingly, pretty close to 13 AMU, but it's not exactly the same. It's 13.0032. And that would be the mass of 13C. So every isotope has a mass associated with it, which, as you see, is not typically a whole number in AMU. Now you might be wondering, why is that? If we saw that, if the mass of 12C is 12 AMUs, doesn't that mean that each proton and each neutron has a mass of 1 AMU? Those two are the same as each other. So why wouldn't the mass of 13C be 13.000, and why wouldn't 14C be 14.000, and so on? So let's get into a little bit of the reasons why this is. This is going to be something you'll come back to at the very end of chemistry too, so we're not going to deal with it a lot. But just to help you understand why that is. So why are the atomic masses of isotopes, why are they not exactly equal to the mass number? And the reason is because of this equation that you've probably seen before, E equals mc squared. And when you form a nucleus, when you take a bunch of protons and neutrons and you smash them together to make a nucleus, you release a lot of energy when you do that. So a lot of energy is released when you form a nucleus. And remember, because of E equals mc squared, if you release energy, you also release some amount of mass. And so that means the individual masses of isotopes are not usually whole numbers, because you're losing some of that mass via energy loss. All right? So when you form nuclei by, again, combining protons and neutrons in some combination, when nuclei form, and this results in a change in the mass. All right. So that's why you're not going to typically have nice whole numbers for the atomic mass of an individual isotope. Except for C12, which is exactly 12, but that's the standard we set to. So then, we have these individual isotope masses, and we can hopefully not be too perturbed by the fact that they're not whole numbers usually. They're often very close to whole numbers, but a little bit different than the mass number. And then what you also have is what's called percent abundance. So if we want to say what is the atomic mass of an element, we have to take into mind what are the masses of the individual isotopes that make up that element, and also what is their abundance. So for each type of element, we're going to have different isotopes that make it up, and they're going to be present in some ratio. So it's the relative amount of each isotope in a natural sample of the element. So if we're working with carbon, it is possible to get a sample that's 100% C12 that would have exactly the atomic mass of carbon-12, which is 12 AMUs. It's also possible to separate out a sample that would be just C13, which would be, the atomic mass is what I gave you before, 13.0032. But in reality, when you take an element in its naturally occurring state and you dig it out of the ground or get it from whatever source it comes from, in reality, it's going to be a mixture of isotopes in almost every case. So the percent abundance is the relative amount of each isotope in a natural sample of the element. So if we take carbon out of the ground, or in any form that we can find carbon in, what we would see, just as a random example, is that in carbon there's going to be about 98.89% C12. So most of carbon is made up of the C12 isotope, but the rest of it is made up of C13. There's even a tiny bit of C14, which is radioactive, and we use that for carbon dating, which you've probably heard of. But within two decimal places, 100% of carbon is either 12C or 13C. Okay? So you have a mixture of the two, and that's going to be true of just about every element. There are maybe a few elements out there that only have one naturally occurring isotope, but almost every element on the periodic table has two or more naturally occurring isotopes, and they have different ratios, different abundances that are characteristic of that element. And then when we want to find what's the atomic mass of that element, we can get the atomic masses of individual isotopes, but if we want to know what's the atomic mass of an element, we use the weighted average of the isotope masses. All right, and remember that we're often going to give it to you as isotope percentages, as I did here. Remember that percentage is the amount out of 100. What we really need to calculate a weighted average is the fraction, which would be the percent divided by 100. So this is isotope percent, but what we really need is isotope fraction, which is the percent divided by 100. And so if you have multiple isotopes, you take the fraction of one isotope and multiply it by its mass. You add to that the fraction of the second isotope, multiplied by its mass, and so on, depending on how many isotopes you have. For most of the problems we give you, you'll have no more than 2 isotopes, but there could be rare times when we expect you to calculate this for 3 or more isotopes. But it's just however many mass fractions however many fractional abundances you have, multiplied by the mass of that specific isotope, and you just add them up. So it's what's called a weighted average, and that's how we report atomic masses then for naturally occurring elements. All right. So if we want to do a sample problem, if we have the element boron, which is atomic symbol B, again, there's no way of knowing these individual isotope masses or the abundances. We will either, if you need them, we'll give them to you in the problem, or sometimes you'll have to solve for one of the abundances or isotope masses as your unknown using that same relationship I just showed you. So these numbers are just tabulated. So you have 2 isotopes for boron, boron 10, which is 10.01294, and then you also have boron 11, which is 11.00931. Again, not exactly equal to the mass number because of E equals mc squared. And then we have the respective abundances, so they're about 20% and 80% roughly for those 2 isotopes, and that makes up all of the naturally occurring boron in the periodic table. Sorry, on Earth. There might be other planets and other solar systems where the isotope ratios are different, but the ones that we quote are obviously on the planet we live on, which is Earth. Or I think most of us do anyway. All right, so then if we want to find the atomic mass of boron, again, it's going to be just the mass fractions, not the mass, I keep saying mass fraction, we're not doing that anymore. It's the fractional abundances of each isotope multiplied by the individual masses. So the atomic mass is going to be the fraction of boron 10 multiplied by its mass plus the fraction of boron 11 multiplied by its mass. All right, now we have to find fractions. Remember, we usually give you percentages, but the fractions are the percentages divided by 100. So if we want to find the fractional abundance is the more complete term of 10 boron, the 10 isotope, it's going to be the percentage, which is 19.90, and we divide that by 100 to get fractional abundance. Now again, there's a good way to check yourself if you forget to convert percent to fraction, because if we use the percentages in this formula up here, we're going to get an atomic mass that's several times, close to 100 times bigger than our isotope masses. So your atomic mass should be in between the isotope masses. So we have isotope masses of about 10 and 11, so the atomic mass should be somewhere in between there, not larger or smaller than that. So that's the fraction of boron 10, and then similarly for boron 11, it's just this number divided by 100, which is 0.8010. All right, so those are the two fractional abundances, and then we just multiply them by the isotope masses and add them. All right, so it's 0.1990 for the first isotope multiplied by its mass, which is given as 10.01294. Fraction of the second isotope is 0.8010. The fractions have to add up to 1. The percentages have to add up to 100. That should be no surprise. Then we multiply that by its isotope mass, which is 11.00931. So we get 1.993 plus 8.818. And when we add these together, we get 10.811 AMU. So the atomic mass of naturally occurring boron is 10.811, and this would be the number you would find in the periodic table. So now the the thing that we sort of glossed over before when we were talking about periodic table, which is these atomic masses. If we go to boron here, we see that the number underneath the atomic symbol is 10.811. That's the atomic mass of boron, which is the weighted average of all of its isotope masses. So these numbers on the periodic table represent, again, naturally occurring samples, and this is the weighted average atomic mass of all the isotopes of that element. And that's how we calculate it, is what we just did here. Okay? So that's how we calculate atomic mass. We can do one other sample problem which requires us to use the same relationship, and now we have to solve for the percent abundance. So we're talking about chlorine now. And if we go to the periodic table, we would see that the atomic mass of chlorine is 35.45. That you can read off the periodic table. And its two naturally occurring isotopes are chlorine 35, which has this atomic mass, and chlorine 37, which has that atomic mass. Again, close to the mass number, but not exact. And we want to know what is the percent abundance of 35Cl. So in this problem, technically we have two unknowns, right? Because we know the masses of each isotope, but we don't know either of their abundances. So we're going to call those our unknowns. So the fractional abundance of 35Cl we'll call X. So again, if we have unknowns, we can use sort of the algebra conventions of calling them X and Y. Fractional abundance of Cl37 we're going to call Y. All right, and if in algebra, if you've taken that, which I hope you have, because it's required before you take this course, remember if we have two unknowns, we need two equations, right? So the relationship that we've just been talking about is that the atomic mass is equal to the weighted average of the isotope masses. So this number 35.45 is going to be the mass of each isotope multiplied by its abundance. So the mass of the first isotope is 34.96885. multiplied by the abundance of that isotope, which we're calling X. We have the mass of the second isotope is 36.96590 multiplied by the mass of the second, the abundance of the second isotope, which is Y. So that's one equation with our two unknowns, where again it's atomic mass is equal to isotope mass times abundance plus isotope mass times abundance. We only have two isotopes, so we stop here. And then finally, we need another relationship for X and Y. So what has to be true about X and Y if they're fractional abundances? Yes, so the percentages added together would have to equal 100. We're talking about fractional abundances, so they would add together to be 1. So X plus Y would be equal to 1. So that's our other equation. Okay? So we have two equations, two unknowns. That means Y is equal to 1 minus X. We're solving for 35Cl, which is X. So the fastest way to do that is to make this substitution where we say Y is equal to 1 minus X. We put that in there. We place that Y with 1 minus X. And so we get a new equation, 35.45 is equal to that mass times X, 96885, plus the second mass, 36.96590 times 1 minus X. And then this is going to require a little bit of algebra, but we can solve for X pretty easily now because this is just a linear equation. All right, so I'm going to skip some of the steps here, but this should be straightforward now, and say that X is equal to 0.7590. Remember that we're looking for here the percent abundance, so we have to take our fractional abundance and multiply it back by 100 to get it back to a percent. So the percentage would be this number times 100, which is 75.90%. So that means naturally occurring chlorine has about 75.9% of the Cl35. The other 24.10% would be Cl37. They average up to give you 35.45 for the atomic mass. Yeah.
Whenever you give us questions like this, are you always going to give us all the possible isotopes? Because that's the only way we know them.
Yeah. So for problems like this, we can only do it. Yeah, we have to either give you all the isotopes. We're not going to have you solve for 3 unknowns. So. Don't worry about that. But if in this type of problem there's 2 unknowns, the 2 abundances, that's as complicated as we'll get. Now you might have to do a problem like this with more than 2 isotopes, but that's just multiplying and adding, so not too difficult, of a step beyond that. But for problems where we have to solve for an unknown, either an unknown abundance or an unknown mass, if one of our isotope masses was the unknown, in that case we'd limit it to 2 isotopes. Okay? Other questions? All right, so that's the definition of atomic mass. Now what we're going to learn is, what's really the value of atomic mass when we're talking about measuring chemical substances. And that relates to then a new concept called the mole, which some of you have probably heard of. Now it's not an animal, as it turns out. But it's a counting word that we use in chemistry. Now, depending on how familiar you are with American vernacular, you've probably heard of some of these counting words already. And they refer to a number of things that we have. So we've heard of probably a dozen before, which is 12. If we have a gross of something, not as common, but that's 12 dozen, which is 144. A score would be 20. Remember when Abraham Lincoln said 4 score, and was it 7 years ago? He was talking about 87 years ago, so that's a score. 1 score is 20. So those are counting words that we have in the English language for telling us how many things we have. And the mole is exactly the same thing. It's a counting word that tells us how many things we have, although it's what we use in chemistry for really tiny things primarily. Because how many things are in a mole, it's going to be this special number here that you've probably seen before if you've taken chemistry, which is 6.022 times 10 to the 23rd. So there are 6.022 times 10 to the 23rd things in 1 mole. And I'm emphasizing here that we can use Avogadro's number, as this is called. We can use this to count any type of object. It doesn't have to just be atoms and molecules, although, as we'll see, it's a very huge number, so it's really only useful for very tiny things like atoms and molecules. And what's important to realize is that when we use this number, it's that number of fundamental particles for that substance, right? So we're going to get into this in more detail, but if you have an element and you have 1 mole of an element, that means you have this many atoms because elements are made up of atoms. If you have a covalent compound instead, let's say water, H2O, if you have a mole of water, you have 6.022 times 10 to the 23rd water molecules, because molecules are the fundamental building block of water. So it's whatever your smallest building block is, your smallest piece. 1 mole is 6.022 times 10 to the 23rd copies of that, or that's how many we count for 1 mole. Now, I want to give you an idea of how big this number is. I think an exponent of 10 to the 23rd looks impressive, but just to sort of emphasize this a little bit, here's a little fun thought experiment. All right, so let's say we had 1 mole of M&Ms, which is probably more than ever existed in the history of the world, but let's say we did, and we wanted to stack them to cover the entire United States of America. So we're going to lay down a nice, even layer of M&Ms. We cover the United States, and then we keep stacking them until we use the entire mole, okay? So we're not going to go through the calculations in detail, but essentially if we assume that the volume of 1 M&M is about 1 cubic centimeter, the area of the United States is about 3 times 10 to the 6 square miles, and then we have to convert that into the same units, obviously. So I'm not going to go through all the conversions, but we'd have to convert this into square centimeters. And what we would find out then is that if we're going to cover the entire United States with M&Ms, and we're going to keep stacking them until we run out of that 1 mole of M&Ms, any guess on how high of a stack of M&Ms we would make? What did someone say? 4 layers of M&Ms. I don't know how many layers it's going to be, but let's talk about how tall that would be. So 4 layers would be about 4 centimeters. So we have a guess of about 4 centimeters. Any other guesses? All right. I don't think anybody's going to get it right because the correct answer is 50 miles. So that's how big of a number moles is. We'd have to cover the entire United States with a stack of M&Ms 50 miles tall to use up 1 mole of M&Ms. So again, we don't use it for regular sized objects because it's just an astronomically large number. That, in terms of number of layers, it's not 4, it's not 8, it's 8 million. So that's how many layers it would be, is 8 million. Okay? So that's basically how big a mole is. Now here's another demonstration of that. So let's say we wanted to empty all of the water out of all the world's oceans, and we use a teaspoon to do it. So we took out 1 spoon at a time and figured out how many teaspoons that was. All right, so the volume of the oceans is about 1.3 times 10 to the 9th cubic kilometers. Again, weird units here, and we have to convert all these English and metric units together. But what it means is that if we wanted to figure out how many teaspoons that is, that's about 2.65 times 10 to the 23rd teaspoons, which is around 1 mole, or about half a mole, I guess, if we're being precise. But basically, there's 1 mole of teaspoons of water in the entire world. Or another way of thinking about this is there's basically the same number of water molecules in 1 teaspoon of water as there is teaspoons of water in the entire world. So, wrap your head around that for a while if you want to go on a nice, chemistry trip. All right, so that's some just little examples that just tell us how big the mole is compared to numbers that we normally count with. All right. Now, what's important about the atomic mass and is how it relates to the mole. So we've talked about atomic mass and sort of the textbook definition of it, and we said that that could be the mass of one atom would be that many AMUs, or the weighted average of all the isotopes is some amount in AMUs. But the other way that we interpret atomic mass, and the way that we typically are going to use it, is that the atomic mass represents the mass of that element in grams that is contained in 1 mole. So the atomic mass represents the mass in grams of 1 mole of an element. All right. So when we did that example problem earlier where we determined the atomic mass of boron, we saw that it was 10.811 AMUs. Another way of interpreting that is saying that 1 mole of boron has a mass of 10.81 grams. And this is why the mole is sort of a pretty useful counting number for us in chemistry, because the molar masses of most substances, the atomic mass, if we're talking about elements, is, on the whole periodic table ranges from about 1 gram per mole to about 200 grams per mole, so a relatively, usable amount of substance. So that's the way that we're going to interpret atomic masses, is the mass in grams of 1 mole of that element. So that now gives us 2 conversion factors involving the mole. So this whole chapter, especially these next 2, even beyond that, these 2 chapters in the book where we're talking about amounts of substances and chemical reactions, especially, is going to be a lot of conversion factors. And now we have the first 2 that we're going to use a lot. So using the mole as our definition, we have 6.022 times 10 to the 23rd atoms, or if in the case of compounds, molecules, or in a more generic sense, things, whatever things we're counting, per 1 mole. So we can use this as a conversion factor. The abbreviation for mole is just MOL. It's probably the world's lamest abbreviation because they just took off the last letter and it doesn't change the pronunciation at all. But it's that's what how we're going to abbreviate it. So we have this conversion factor here, which is Avogadro's number of things, number of atoms or molecules per 1 mole. And then, as we just learned, if we're talking about elements, the atomic mass of the element is the number of grams that element contained in 1 mole. All right, so we have now 2 relationships, one involving the number of atoms or molecules, one involving the mass of that element as it relates to moles of that element. So these are, again, important conversion factors, especially the bottom one here. We don't usually need to think about how many individual atoms or molecules are in this sample of chemical that I have, but it is very common to use the relationship between mass and moles when we're trying to measure out substances in an experimental setting, as we'll see through a number of the example problems we do. All right, so those are the 2 relationships. Now let's just look at a few different ways that we use them. Okay? So before there was a crisis in helium shortage, we could have gotten a helium cylinder. I suggest not wasting it to blow up balloons because it's very important for a number of research and technology applications, so we don't want to waste it on balloons. But anyway, if we had a cylinder of helium used for balloons or otherwise, we could determine that it has 239 moles of helium. We want to know how many helium atoms are in the cylinder. So this is a pretty straightforward application of that first conversion factor. And again, just like we've done before for some of the unit conversion problems that we've had, we haven't had a ton, but we're going to start really amping it up now. The number of helium atoms, we start with the given quantity. So again, what's helpful to do is write down what we're looking for, because eventually, and we're even going to get to some today that have more than one step. So if you write down what you're looking for, you'll know how many conversions it takes to get there. So if we're looking for the number of helium atoms, what we're given is that we have 239 moles of helium. And again, we now have a relationship. We're looking for number of atoms, how many atoms. We're going to use Avogadro's number. And again, we want moles of helium to cancel, and we want the number of atoms to be in the numerator. So that tells us that we write Avogadro's number in this way, 6.02 times 10 to the 23rd helium atoms per 1 mole. So that moles cancel out, and that gives us number of helium atoms. So we get 1.44 times 10 to the 26. So in 1 cylinder of helium, you have this many helium atoms. Again, a huge number. Okay? So this, again, a one-step simple problem, but when we're counting individual atoms or molecules, so a lot of times, the trick to doing this problem is we have, we're going to have a lot of relationships involving the moles, and it's like, well, which one do I use? How do I know? So if you look at the problem and it wants to know how many atoms, how many molecules, how many particles, how many ions, whatever the case is, you should automatically zero in and think that Avogadro's number is going to be a part of that conversion. In this case, it's the only part of that conversion. So we're going to just use Avogadro's number. And in this step here, when we're just converting from moles of substance into the number of atoms or molecules, the identity of the substance doesn't matter. Okay, because Avogadro's number applies for every single substance, every pure substance in the world. So it doesn't matter that this is a helium cylinder. If this was a nitrogen cylinder, an argon cylinder, or a carbon dioxide cylinder, the conversion would be exactly the same. It's independent of the substance. So for these types of conversions using Avogadro's number, the identity of the substance doesn't matter, at least for that particular step. As we'll see later on, sometimes that comes into play, the chemical formula or identity of the substance, but in terms of this step of just using Avogadro's number, it doesn't matter what it is. It's the same number for every substance, 6.022 times 10 to the 23rd. Okay? So that's what we have for just using Avogadro's number to find number of atoms, or we could do it for compounds, number of molecules. Let's do a little bit different one. So now let's say we have a gold coin. So imagine that you're concerned about the end of the world and you start buying up a bunch of gold and you get a gold coin that looks like this. And the standard American gold bullion coin contains 31.1 grams of pure gold, which is atomic symbol AU. How many moles of gold are in the coin? Now, in this case, we're giving you a mass, so we should think that we need to use not Avogadro's number, but actually the atomic mass of the substance, or more generally the molar mass, the amount of mass in 1 moles. And in this time, the identity of the substance matters because every substance has its own characteristic molar mass. So if we want to find the moles of gold, which is what we're looking for, we again start with the given information, which is, in this case, 31.1 grams. Now, we have a conversion that allows us to do this in one step. Again, grams to moles, we're just going to use atomic mass. But we have to know, do we multiply or divide by the atomic mass? And again, that's where the units will come into play. So we want moles of gold in the numerator and then grams in the denominator so that that cancels out. And so that means we're actually going to put the atomic mass in the denominator because it's grams per mole for the atomic mass. So we have to find out what that is. And again, if we're not told what it is, we go to the periodic table. So gold is atomic number 79, but what we need for this conversion is the atomic mass, which is the bigger number below that. So the atomic mass is going to be 196.97, and so that's the number we're going to use to do this conversion. Okay? So we have 1 mole of gold has a mass of 196.97 grams. All right, so it's grams per mole, so that means grams cancel out. And this tells us that 1 coin of gold, this 31.1 gram coin, has 0.158 moles of gold. All right, so this is a little bit different now. When you're converting mass to moles, which we did here, you need to know the identity of the substance because each substance has a characteristic atomic or molecular mass. All right, so here, if it was a different substance besides gold, we would have had to put a different number here in the denominator. That's the atomic mass of that element, or as we'll see later on, if we're talking about molecules or compounds, the molar mass of that compound, which we'll cover a little bit later on. Okay, so any questions on these two? Just simple one-step conversions. And again, as we move forward in the course, typically these types of calculations are going to be parts of much larger series of conversions. So we're going to build up the complexity as we go along. All right, now let's do one that does involve multiple steps. Some of the information in this problem may or may not be useful. So recently in chemistry, somebody discovered what's called a nanoparticle. So it's a huge molecule that has a lot of atoms in it, and it has a diameter of 1.3 nanometers, and it has 37 indium atoms in the structure. So indium is the metal that's in this structure. And we want to know what is the mass of one of these particles. So now we're trying to find the mass of a single particle that has 37 indium atoms plus some other things around, but we want to know the mass of indium specifically. So here we don't really have an easy conversion for this, at least not a one-step, because we're looking for the mass in grams. So we're looking for the mass of indium, In. We know that we have 37 atoms. But do we have a easy conversion factor that allows us to go from number of atoms to number of grams? A one-step anyway. No, remember that right now we can go from number of atoms to number of moles, we can go from number of moles to number of grams, but there's no one-step conversion that goes from number of atoms to number of grams. So what we're going to do then is do this in 2 steps. So if we have the number of atoms, we can convert to moles first. So moles in the numerator, number of atoms in the denominator. So this time we're going to divide by Avogadro's number because 1 mole has 6.022 times 10 to the 23rd atoms. So that cancels out atoms. But now we're still in moles. Again, writing down the units and paying attention to where we are and where we're going is always helpful. We want to go to grams. If we have moles, we can then use the atomic mass. So I'm going to go to a separate line here. We want moles to cancel out now. And we want to use the atomic mass of indium in the numerator to find how many grams of indium are in 1 mole. All right, so that again comes from the periodic table. Indium is number 49. The atomic mass is 114.82 grams per mole. So we're going to use that as a conversion factor, 114.82 grams per 1 mole. And so when we multiply these across, moles now cancels out, and we're left with grams of indium, which is exactly what we want. And what we get is 7.05 times 10 to the minus 21 grams. So again, a very tiny number because it's just 37 atoms, which isn't very many, but that's the number we would get. So this hopefully demonstrates that in many cases we're going to have to do multiple conversions to get between different quantities that we're interested in. Also that we can use these conversion factors either in 2 different ways, either with moles in the numerator or atoms in the denominator, or vice versa. We used this one in the opposite way earlier. So these unit conversion factors can be written as ratios in either order because they're equal to 1 basically, and we have to use the units that we're converting between to figure out whether we multiply or divide and how to do that. So it's called the factor label method, which is how I'm going to do all of these. All right, questions on this one, a little bit more complex, but again, just the same 2 steps, but now combined with a little bit in a little bit different order. Okay. All right, so that gives us. We'll just do one more now, just to really drive home this point. So now let's say we really were, concerned about the fate of the world, so we started investing in gold bars, not gold coins, assuming you had enough money to even buy one of these because they cost a lot. So a gold bar weighs 12.4 kilograms. We want to know how many gold atoms are in a gold bar. All right, so again, we're looking for number of atoms, so we should recognize that we're going to use Avogadro's number, but we can't do it again directly because we're given a mass. And whether the mass is in grams or kilograms, we don't have a conversion that goes from mass into number of atoms directly. So it's again going to be a multiple step conversion. So we're looking for the number of gold atoms given that we, in this case, have 12.4 kilograms. All right. We have to remember that atomic masses are in grams per mole. So in any case that we're given a unit other than grams, we have to convert into that first. So we're going to convert into grams of gold. Kilograms in the denominator so that it cancels out. The conversion for grams to kilograms is 1,000 grams per 1 kilogram. So we have 12,400 grams of gold. We want to figure out how many atoms are in there, and again, it's going to be a 2-step conversion. We go first to number of moles. So we want grams of gold to cancel, moles of gold in the numerator. So we're going to use the atomic mass, which is 196.97. We looked that up earlier from the periodic table. That's per mole of gold. So that gives us into moles, and a lot of people make the mistake of stopping here. But remember, number of moles is not the number of individual atoms. It's that's going to be Avogadro's number that gets us to that. So we don't stop here. We have to do one more step and figure out how many gold atoms are in there. So mole in the denominator so that it cancels out with number of gold atoms. And this will be, again, Avogadro's number, 6.02 times 10 to the 23rd per 1 mole. Okay? So we have to use a series of steps this time, and we get 3.79 times 10 to the 25th atoms. Okay? So almost the exact opposite of the last problem we did. Last time we went from number of atoms into mass. This time we went from mass to number of atoms. So we just reversed the steps, but we also started with kilograms, so there's this additional first step of converting to grams. So any questions on conversions involving moles? That's sort of the basics of it. We're going to get at the complexity soon, so let's just address any of those questions now before we move on. Okay. So the next section we're going to talk about is if we have, instead of elements, we have compounds, we have a more generic term called molar mass. And so the molar mass, we saw for elements, it's just the atomic mass from the periodic table tells us how many grams that element are in 1 mole. If we want to do it for a compound, we have more than one element present, so we can't just use the periodic table and look it up directly. So the definition of molar mass, as the name implies, is the mass of 1 mole of a compound so again, it's a ratio or a conversion of grams per mole. It has a lot of synonyms too, so let's not be confused by terminology. Let's realize that molar mass is probably the most general and appropriate term to use in these, but it has a lot of different ways that we call it. So molecular weight is one that we use. Formula mass or formula weight, especially for ionic compounds, because ionic compounds don't really consist of molecules, so calling it molecular weight for an ionic compound is at least not very precise, even though from a numerical standpoint you calculate it the same way. And there's some abbreviations as well. Our book doesn't do this, but the old textbook did, so you might see this on some of the homework questions, this sort of weird looking capital script M. So sometimes there's a big M that looks kind of like a cursive M almost, or sometimes MW, which again means molecular weight. So a lot of different things of calling it the same thing, but again, it's just the mass of 1 mole of a compound, whether it be an ionic or a covalent compound, doesn't matter, we calculate it the same way, as we'll see. So the way we calculate it is not terribly difficult. We just add together the individual atomic masses. So we have to know the chemical formula of the compound. We can't do it without that, but if you know the chemical formula, you just take the individual atomic masses that make up that formula and add them together. Okay, so you have the chemical formula either given to you in the problem, or if we name the compound, you figure out what formula corresponds to that, and you add up the atomic masses, and that gives you then the molar mass or molecular weight or whatever you want to call it of that compound altogether. Okay, so relatively simple to do, but we are going to have to do it a lot because we're going to use molar mass a lot. So let's say we have the compound glycine, which is one of the 20 or 19 amino acids that we have in our body. We want to know what's the molar mass of this. So the chemical formula is C2H5NO2. So that's the chemical formula. And what we have to recognize is that we have to just add together the individual atomic masses, but we can't forget about the subscripts here. Okay? So what these subscripts tell us is that 1 mole of this compound, C2H5NO2, is going to include 2 moles of carbon, because carbon has a subscript of 2, 5 moles of hydrogen, because there's a subscript of 5 on H, 1 mole of nitrogen. If there's no subscript, that means there's just 1, and it's going to have 2 moles of oxygen. So if we want to figure out then the molar mass of this compound, we have to account for all of these masses. So it's not just the individual elements, but how many of them there are in the formula. Okay, so we have to make sure we account for the fact that there's 2 moles of carbon, 5 moles of hydrogen, and so on. So when we calculate molar mass, we take the subscript in the chemical formula, which is going to be 2 for carbon, and we multiply that by the atomic mass. So the individual atomic masses we do get from the periodic table still, so CH, N, and O. So carbon is here, 12.011. That's the weighted average atomic mass of naturally occurring carbon. So we double that for carbon. We have 5 hydrogens. Oh, geez.
Wow.
All right. For those of you watching at home, that was a rumble of thunder that I don't think was an earthquake or anything worse than that. All right, let's refocus our efforts. It's not like we haven't seen thunder if we lived in Houston for more than a week. So, all right, so let's go. We have hydrogen as the next element. We have the atomic mass of hydrogen is 1.008. More decimals there than we really need. So 1.008 grams per mole for hydrogen, and there's going to be 5 of those in the formula, so we have to multiply that by 5. So that's hydrogen. And then we have 1 nitrogen. I'm not going to go back to the periodic table a million times, but the nitrogen's atomic mass is 14.01. That's the number on the periodic table that we'd find for nitrogen. And then we have 2 oxygens, so we're going to double the atomic mass of oxygen, which is 16 grams per mole. So we just add all those together, and we get 75.07 grams per mole. So that means 1 mole of glycine has a mass of 75.07 grams, and we get that just by, again, determining the individual atomic masses and adding them together. All right? Any questions on that? All right, very similar example. So we have the formula of lead-4 sulfate. So this is where we once again can't just forget about our nomenclature, because there are going to be problems like this, or more complex ones, where we give you the names of compounds, and you have to be able to then convert that into a formula. So if we have lead-4 sulfate, do I have that one in here? I don't know why I changed it. So lead-4 sulfate, we have lead is Pb. I should have said that in the formula, in the problem, because that's not one we have to know. And it's going to be Pb plus 4. Sulfate is SO4 2 minus. So the correct formula for lead sulfate is going to be PbSO4 2. Sounds like it's pouring now. Great. All right, so we have lead sulfate PbSO4 2, and we want to find the formula mass of this. But one reason I'm showing you this one is just to make sure that we're clear on how we do this. So this formula has 1 lead, and the atomic mass of Pb is, that one I don't remember off the top of my head, 207.2, which is that number there, underneath the atomic symbol. But then we have to remember, when we have these polyatomic ions, we have these subscripts outside the parentheses. So we have 2 copies of SO4 2 minus. So really all that's present in this formula is going to be lead 4 plus, and then 2 SO4 2 minuses. And so what we have is actually a total of 2 sulfurs, because we have 1 sulfur in each sulfate, but we have 2 of them in the formula. So we have 2 times sulfur, which is 32.07 grams per mole from the periodic table. And then if we do oxygen, we have to add the contribution from oxygen. There's 4 oxygens per sulfate, but there's 2 sulfates for the whole formula, so that's a total of 8 oxygen atoms. So make sure when you're counting up the chemical formulas of polyatomic ions, we remember that if we have more than one of them and there's these parentheses around it, that whole thing is taken twice. So that's a total of 8 oxygens, which still has an atomic mass of 16 grams per mole, as we saw in the last problem. So that's oxygen. And then when we add these together, I stupidly forgot to calculate this beforehand. So I changed the problem for some reason. And, oh, here it is. 399.34 is what I got. All right, so a much bigger number that time for lead sulfate. Lead's a pretty heavy element, as you would imagine. And we have to make sure, again, we account for the fact that there's 2 SO4, 2 minuses. That gives us a total of 2 sulfurs and 8 oxygens. All right, but same story. Any questions on this one? Yes? Yes, but for ionic compounds, we always want them in the lowest whole number ratio. So if we just switch the charges, we would get Pb2SO4 4. But 2 to 4 is not the smallest ratio. It would be 1 to 2. So we still have to reduce it to the smallest ratio if we use that approach. So that's how that goes to there. Okay? So good question, but we have to remember we always want lowest whole number ratios anytime we're dealing with ionic compounds. All right? Anything else? All right, last one. So this was a compound that one of the graduate students I work with prepared in the research lab, and it gives off red light, as you can see. So this compound has a molar mass of 774.94 grams per mole. So here I'm giving you the molar mass, and I want to know how many molecules of this compound are in a 1 gram sample. So if we make 1 gram of this iridium compound, has a molar mass of 774.94, how many molecules is that? So this time we're going to be using the molar mass as a conversion factor, which is often what we're going to do. We're not going to give you a lot of problems where we just say, calculate the molar mass and be done. We're going to actually have that as a conversion factor that we need to use for solving this problem. So this approach is almost identical to some of the ones we did earlier with elements, but now we're just dealing with compounds, but it's the same concept. So if we're going to look for the number of molecules, we should once again think of Avogadro's number because we're looking for the individual number of molecules. We're counting up all the molecules in the sample. And we're starting with our given information is that we have 1 gram of compound. So typically we don't start with conversion factors when we're doing these. We start with a given amount, which is 1 gram, of whatever this iridium compound is. I'll just say iridium in brackets to abbreviate it. It has a more complicated formula, obviously. A lot of there's carbon, hydrogen, nitrogen, and oxygen also in this formula, but I didn't give you the full formula. But we know that the molar mass is 774.94. So if we have grams of compound, we can convert to moles using the molar mass. So 1 mole of this compound, grams in the denominator so that they cancel out. 1 mole has a mass of 774.9. So 774.9 grams of this compound in 1 mole. That's the given number in the problem, grams per mole. And then we're going to use in a separate step Avogadro's number. So this gives us the moles of compound, but what we want is the number of molecules. So in a separate step, we're going to take molecules of iridium on the top, moles in the denominator so that it cancels out. I always like to write the units first so that I know which order to put the numbers in. So moles cancel, and in order to do that, we have to use Avogadro's number, 6.022 times 10 to the 23rd. So remember that for covalent compounds, the simple building block is molecules, so that we're going to have 6.022 times 10 to the 23rd molecules of this compound for every 1 mole. So we have a 2-step conversion similar to what we did before, and we get 7.77 times 10 to the 20th molecules. All right. So again, if we're counting individual atoms and molecules, we often get very large numbers. We're talking about sort of human-sized samples of these compounds. All right, same series of steps, so just for a compound instead of for an element. All right, the last thing I want to cover today is going back to mass percent. So this is one of the first topics we covered in this course. We talked about it in the context of the law of definite composition and to some extent law of multiple proportions. A lot of the ways that early scientists classified compounds was in terms of the mass ratios or mass percents of the elements in those compounds. And so we're going to come back and review this, and we're going to see now how does mass percent relate to the chemical formula. So we've been talking about chemical formulas today and molar masses, and there actually is a relationship between mass percent and chemical formula. The early scientists didn't realize this. This wasn't until later on when we really had a more refined view of atomic theory and until Avogadro's number came along. As an aside, I'm pretty sure, so Avogadro's number is named after a scientist named Avogadro, who we will learn about later on when we talk about gas laws. We already introduced him a little bit earlier. He came up with the idea that in a given volume of gas, you have the same number of particles no matter what the gas is. That's Avogadro's law, which we're going to cover in more detail. He didn't, as far as I know, actually discover Avogadro's number. It's just that somebody else discovered it and apparently had a man crush on Avogadro, so they named it after him. But he wasn't actually the one that discovered Avogadro's number, despite the fact that it's named after him. So a little history for you there. But we're going to see today, now that we know what Avogadro's number is, now that we know what a mole is, we have a relationship between chemical formula and mass percent, and we can really go in both directions. If we give you the chemical formula of a compound, we can use that to calculate the mass percents of all the elements in the compound. Or if we give you the mass percents of all the elements in the compound, we can back out a chemical formula going in both directions. So we're going to learn how to do that next and see that relationship to some of the things we learned very early on. So as a review, the mass percent for any element in a compound is just going to be the mass of that element, which I'll just again abbreviate generically as A, divided by the mass of the whole compound, multiplied by 100, again, because it's a percentage. Okay? And what we're going to do, as I said, is we're going to work in both directions. I think today we're just going to do going from from molecular formula to mass percent. Next time we're going to see the opposite approach, going from mass percent to molecular formula, so it works both ways, as I said. And typically when we do this, we assume whatever amount of compound is convenient for us to assume. So if we're given the molecular formula, the easiest thing for us to do is to assume we have 1 mole of that compound. Because if we assume we have 1 mole of compound, we know exactly what the mass of that compound is going to be from its molar mass, as we just talked about. So if we assume we have 1 mole of compound, because remember, these mass percentages, they don't depend on how much substance we have. We could have, 1 speck of this compound, or we could have a huge pile of it, and it's going to have the same mass percent, because mass percent is a ratio. It's not an absolute quantity. So if we assume we have 1 mole of compound, the mass percent of that element is going to be the mass of that element in 1 mole divided by the molar mass of the compound and essentially what we're doing here, we're going to work through an example next that'll really illustrate this, but essentially what we're doing here is we're going to say that we know the mass of 1 mole of compound is just the molar mass that we calculate from the formula, and we're going to figure out how much did that element contribute to that molar mass, because the molar mass is the sum of all the elements in the formula. So what portion of that molar mass came from that specific element? We divide the two, multiply by 100. That gives us the mass percent of the element. So now anytime we have a chemical formula, we will be able to calculate what the mass percent of that is, as I'll show you now. So let's go back to that same compound glycine, C2H5NO2, and we want to know what's the mass percent of carbon in glycine. We could do this for any or all of the elements. So we could do it for carbon, we could do it for hydrogen, nitrogen, or oxygen. Same approach, just we have to use that specific element. So if we assume that we have 1 mole of glycine, and again, if we're given the chemical formula and trying to find the mass percent, this is the convenient way to do it, because we know if we have 1 mole of glycine, we saw that in the last example we did with glycine, the mass of that is going to be 75.07. So this is the molar mass of glycine that we calculated before using, again, the sum of the atomic masses of carbon, hydrogen, nitrogen, oxygen, multiplied by how many of them there are in the formula. So that's the mass of 1 mole. So that gives us our denominator in the mass percent calculation. And then if we want to know how much carbon is in there, we're looking for the mass of carbon in this 1 mole. It's just going to be that piece of the formula that we use to calculate molar mass. So carbon has a subscript of 2, so that means 1 mole of this compound has 2 moles of carbon. And we use the atomic mass of carbon because it's an element to figure out what mass does that correspond to. So if we go back to the periodic table, as we saw, the atomic mass of carbon is 12.01 grams per mole. So we have 12.01 grams of carbon in 1 mole of carbon. So that means 2 moles of carbon has a mass of 24.02 grams. And now if we want to find the mass percent of carbon, we now know in 1 mole of compound that we have 24.02 grams of carbon, mass of the element, divided by the mass of the compound, which is 75.07. That's the mass of 1 mole of that compound. So mass of element divided by mass of compound, multiplied by 100 to give it to a percent, and we get 32.00%. So that means out of the whole mass of glycine that we have, no matter how much of it there is, 32% of that mass is going to be made up of carbon, and we could do the same for the other elements. They would all add up to 100. So next time we're going to see how to go the other way, which is taking given mass percents and converting those into chemical formulas, just working these steps in reverse. And we'll also move on to some more complicated things as well. All right, so I'll see you guys on Wednesday. Have a good next couple of days.